So the last type of problem that we're going to do resembles problem number 13 in your in-class problem packet. And the question simply asks, use the thermodynamic data to estimate the normal boiling point of water. So in other words, yes, we're going to have to use that big old chart, but now they're asking us to produce a temperature. So in the last problem set, they asked us to determine whether or not the chemical reaction was going to be spontaneous at a specific temperature. So in other words, hey, what's the delta G value? Here's the temperature. In this style of problem, they're saying, hey, you should know the delta G value at a boiling point, and we want the temperature. So it's just kind of the reversal of the same style of problem. The only really big point of understanding that you need here is that a boiling point is a very magical temperature between a state of not boiling and boiling, the state between where you're going to have a liquid and a gas. So thermodynamically speaking, we say that the delta G value at that one magical temperature is 0. You're at equilibrium. So you're kind of in that half state between you haven't boiled yet, you're not really a liquid, you're not really a gas, it's just this is the moment where it's going to start happening. So for all problems where they're asking us to calculate a specific temperature, usually of this type of change, we put in a delta G value of 0. So again, anytime that you're asked for a temperature, delta G equals 0. Now let's proceed, because this honestly is not all that difficult a problem. It's almost exactly like the second method that we used in example problem 12, where if we look at the overall equation, delta G equals delta H minus T delta S, it's the only equation that we have that has temperature as a factor. And if I know that I'm going to need to solve for the for temperature, and I know that I have to plug in a 0 for the delta G value, that means I need to calculate delta H, I need to calculate delta S, and then you plug in chug. So it's just a process. These problems, yes, are extremely tedious, but I don't think overwhelmingly very difficult. Here we go. So first step, I'm going to calculate my delta H. So again, that's products minus reactants using heats of formation data right from the thermodynamic list. So I found the value for the H2O gas, that ended up being negative 241.8, minus the H2O liquid, which was negative 285.8. Overall, the difference then is negative 44 kilojoules per mole. So they're saying that this process is essentially exothermic. Now for the second half, the delta S part, again, same equation, products minus reactants, look the values up, plug and chug. The number for the gas water, 188.7, and the liquid water, 69.91, and that makes a lot of sense. Liquid water would be more ordered than the gaseous water, so yes, of course, the S value has to be a little lower for the liquid water. Difference ends up being 118.79 joules per mole Kelvin, and again, immediately convert it into kilojoules per mole Kelvin. So that ends up with 0.11879. I don't think anything we've done here should rock your socks off that hard. So this is just a regular old delta H and a regular old delta S. So now part 2 of the problem, let's bring it all together. We're going to plug our delta H value in. We're going to plug our delta S value in. And again, because we're looking for that magic temperature between liquid and gas, we're going to plug in a delta G value of 0, equilibrium. And here's what it looks like. So again, just reiterating the data for you up top. And then down at the bottom of the page, I filled in my equation. So my delta G value, 0. Delta H value, negative 44 kilojoules per mole, minus temperature, T, times delta S, but in units of kilojoules, so 0.11879 kilojoules per mole Kelvin. When I plugged and I chugged, I solved for my T, and I found that it equaled about 370 Kelvin. And once you convert back into Celsius, it should be about 97-ish degrees. And what I found interesting about this is that that is obviously different than the 100 that we're always taught. Gee, I wonder why that value would be lower. Could it have something to do with work? Could be. I don't know. At any rate, this is the final style of problem that you're going to be responsible for in this chapter. So I want to make sure that you can go through and do as many of your delta G problems as you possibly can, and we will review them tomorrow.